Okay, 3, 2, 1, it's jam.
What's up, science fam? Does light always move in a straight line? Is light really straight, or can we bend light? So not all things are straight, not all people are straight, and light itself can actually be bent in one way or another. And that's what we're going to talk about in this session. My name is Sir Ramon, and this is Science with Sermon. So, our topic is lenses and refraction. It's how light allows us to see the same as properties of light, the subtitle. It's basically because our eyes themselves have lenses that allow us to take in light and be able to see. So what are we up to? We're going to explain Snell's law of refraction. We're going to illustrate how images are formed by lenses and calculate distances using the lens equation. So really fast things tend to move in straight lines. If you've ever seen a cat or a dog that's running around, they're going really fast. Even if they try to turn, they're gonna slip and hit the wall. But light is also fast. Exactly how fast is it? It's so fast that it's actually the fastest thing that theoretically we know of. Technically, going faster than light, or FTL, could be a form of time travel. Because if you're going faster than light, technically you're going to the past in one form or another. Because if you're faster than light, faster than electromagnetic radiation, you're going faster than the light can reach a certain area. It's difficult to explain, but the point is, light is hella fast. But even very fast things slow down when it interacts with matter. As you can see in this GIF, even a bullet from a gun will slow down in water. This physicist is so confident that he stood in front of a rifle, then fired it at himself in a swimming pool. Or he just wanted to die because physics sucks. A change in velocity often results in a change in direction, and that's exactly what's happening when we're refracting light. So refraction is the change in direction of a wave passing from one medium to another. A medium is like an area or a material that something is traveling through. So different media have different refractive indices or index. So that means that if it's a different material, it bends or distorts the speed of light in a different way. Excuse me. So this bending or refracting of light can be described by Snell's law, or the law of refraction. So it relates the refractive index of a material to the refraction angles of light. So generally, the law of refraction, the equation is here. So it's n1 sine theta 1 is equal to n2 sine theta 2. What does this mean? N1 just means the first medium, the refractive index of the first medium. So wherever your light ray is coming from, the refractive index of the first medium will be n1. While theta 1, so this thing, theta 1, is the incident angle, or the angle at which the incident ray is going to your interface. So between the layers of your media, if you make a perpendicular line, so that's the line that you form the angle from. So this line that's perpendicular to the interface, you form the angle there. That's theta 1, the angle of the incident ray. On the other hand, N2 is the refractive index of the second medium, and the refracted angle is theta 2. Sine is a function that we use in physics, science, mathematics. So I won't go into detail on that. You can use calculators in order to solve these kinds of problems. But the case in point is that the concept is, if your refractive index of your first thing is lower than the refractive index of your next thing, that means that if it goes into your medium number 2, it becomes slower. Okay? So again, the higher the refractive index, the more it is able to slow something, the more it is able to bend uh, light or electromagnetic radiation as it passes through the interface. So how can we bend light to our will? How do we control how light is refracted? So it's not ideal to use different materials all the time. There are some cases where we use a different material to remove a refractive index or to control the refractive index. One example is a microscope. the oil immersion objective, one of the objectives on the nose piece. We use oil on the oil immersion objective so that the refractive index is less. So lenses are another way. So instead of different materials, we have different thicknesses of material. So lenses are shaped transparent objects that can refract light to either converge or diverge to or from a certain point. And one example of lenses are the lenses in glasses. So they can make light converge at a certain point. So we have two types of lenses. We have convex and concave lenses. So your convex lenses are the ones that bulge out on both sides and they make light converge to a certain point. Your concave lenses are the lenses that look like they have spoons, the depression of spoons on both sides. So that's your concave lenses. So don't confuse your lenses and mirrors. For mirrors, convex is diverging. For lenses, convex is converging. Okay, so that's why we prefer to refer to them as convex and concave because it's less confusing. You just look at the shape. Convex means it's bulging out. Concave means it's caved in. Okay, so let's try not to confuse ourselves by referring to them as convex and concave. So the anatomy of lenses, when you draw a diagram for lenses, it's similar to mirrors. So we have a principal axis, we have the vertical axis, which is just the vertical line in the center of the lens, and we have the focal length. Now there's also an arbitrary length called 2f. It's just twice the focus. This is like the C from mirrors, but there is no radius of curvature for lenses, particularly for convex lenses. Okay, so we just say 2f instead of C. So same concepts are there though. So how do lenses refract light? How do we predict how images are formed? So these are the rules for refraction for convex lenses. These are very long, but the highlighted things are the key points. So number one, if we have a ray that's traveling parallel, once it passes the lens, it will eventually refract to go through the focal point. If it's going through the focal point before the lens, once it goes through the lens, it will begin traveling parallel. If it's if your ray goes through the center of your lens, it will go through it in the same direction. So let's use pictures to illustrate this point. So let's try making a ray diagram step by step for convex lenses. So in this convex lens, first thing, we draw the incident rays. Again, for incident rays, for lenses, we have three. We have the one that's parallel, we have the one that's passing through the center, and one that's going through the focus. So once you draw the refracted rays, again, after they pass through the lens, the one that's going parallel will then go to the focus. The one that's going through the center will continue in the same direction, while the one that passes through the focus will end up becoming parallel after it passes the lens. Okay? Third, we draw the final image at the intersection point of the refracted rays, and we can draw the image as an arrow, and the arrow will tell us the properties of the image. In this case, it's inverted because it's down, it's smaller because it's smaller than the object, and it's real because the rays intersect at an actual point in space. They're not extended rays, they're actual refracted light rays. All right? So what are the cases for convex lenses? How does the position of the object determine the characteristics of your image? So there are 5 cases similar to your concave lenses. So your concave mirrors, your convex lenses have 5 cases as well. So if it's beyond 2f, the image is always smaller. Your image becomes the same size once your object is on the 2f position. Your image becomes magnified or larger if it's between f and 2f. The moment the object is on the f point, that's your blind spot, the image does not exist. And if it's nearer than the focus point, your image becomes virtual and magnified. So these are the 5 cases depending on the position of your object arrow. But another way to put this is that there's a pattern as the object is moved closer, and the pattern changes as you go towards f. So Going towards F from 1 to 6, so you can see from 1 to 6, this is the object arrow. On the left, the red arrow. If it goes from 1 to 6, your image tends to get larger, right? So it gets larger, but it's always inverted. The moment it hits F at point 6, there's no image. So F is where it zeroes out, where the image suddenly disappears. And if you go beyond F, it suddenly flips beyond, meaning it flips to the other side of the lens. It becomes a virtual image. So after 6, your 7 went to the other side of the image, and then 8 is also on your 7 is on the other side of the lens, and your 8 is also on the other side of the lens. So again, there's a pattern that flips once you get to the focus point, the focal point. So next are the refraction rules for concave lenses, for the lenses that cave in on both sides. So similar to earlier, traveling parallel will end up focal. The one that's traveling to the focal point will end up traveling parallel, while the one that goes to the center will stay in the same direction. So let's use pictures to make it easier. Step by step, let's make a ray diagram. First, the incident rays, same as earlier, make a parallel ray, make a ray that goes through the focus, not through the focus before the lens. In the case of concave lenses, we have to try to make it point to the focus after the lens. And the one that goes through the center will keep going through to the end. All right? So, next is to draw the refracted rays as they pass through the lens. So you can see they don't intersect, which means we have to have a virtual image. And you can see that after the parallel goes through, after the parallel incident ray goes through, the refracted ray would have passed through the focal point before the lens. It doesn't bend toward the focus point on the other end. Remember that it's a diverging lens when it's a concave lens. So your refracted rays should always go farther away from the focus. So same for here. If the incident ray is going toward the focus, it will become parallel. So you're going to have problems if you try to make the ray go through the focus before the lens, because after that, you'll get the refracted ray, but then that refracted ray would be erroneous or wrong because it wouldn't have been diverging properly. Okay? So again, remember for concave lenses, you point it towards the focus after the lens. So next is to just get the image, which you do by extending the refracted rays from their tail. You extend them and you'll get the image on the side to the left of the lens. So your image is upright, small, and virtual, meaning we got it from extended rays. It's not projected in actual space. So your concave lenses only have one case. The closer the object is to the mirror, the bigger the image becomes. But the image will always be small and it will always be virtual. It never ends up on the other side. Alright, so that's why we don't have many examples of concave lenses used in actual technology, because it's virtual images instead. Your convex lenses are common in your glasses, in your cameras, in your projectors. So where's the math though? How do we describe the lengths and the sizes? See, the thing is, if you watch the mirrors video, you should be able to do the math here as well, because the thin lens equation is the exact same as the mirror equation. It relates the distances to the focal length, and it's the exact same formula. Okay, so it also uses the focal length, also uses object and image distance. Your magnification equation is also exactly the same as the equation for the one for mirrors. It relates the height of the image to the height of the object, or the negative distance of the image to the distance of the object. Okay, so let's try later the a sample problem. So again, these are the same math skills that you need. Same steps to solve a lens problem. First, you draw the ray diagram. So for the sample problem, we have a 4 centimeter tall light bulb placed 45, let's change this to 45 centimeters from a double convex lens having a focal length of 15.2 centimeters. Let's change this to 15 centimeters. So we'll determine the image distance and the image size. So first, the ray diagram. Again, we're making the decimals much more exact so that our example will become less complicated. So your distance is 45 centimeters for your object. Your keyword here is placed a distance of 45 centimeters. Your focal length is 15 centimeters. It's given straight up. So in this case, again, in your ray diagram, you need to be able to make note of the case. How far your object is from your lens. Is it beyond 2f, before 2f, and so on. And to get that, if you have the focal length, we just get focal length times 2 for the 2f. So 15 times 2 is just 30, and that's less than 45. So we know that your object is beyond your 2f. So we use this case for your ray diagram. And again, since it's a convex lens, we use the convex lens diagram. Second, get the given. So these are all the numbers with their tell words. So 4 centimeters tall, tall meaning it's the height of your object. The distance of means that it's the distance of your object. And the focal length, of course, it's for f. So we have your given noted down here. Third, what's the question? In this case, it's asking what's the image distance and the image size. So it's basically asking straight up, what's the image distance, di, and what's the image size, hi. Okay, so these are your missing variables. Fourth, what's the formula? We have our two formulas here. We have to check what's given and what's missing. And as we can see, it's easier to start with the thin lens equation first because all the variables are either given or what we're solving for. Let's try that. If we're solving it, so if we substitute it into the equation, if we isolate di by moving 1 over 45 to the other side or subtracting both sides by 1 over 45, we get this equation. If we make them have common denominators, we get 3 over 45 minus 1 over 45. We get 2 over 45 once we subtract. And finally, if we flip and divide, we get 22.5 centimeters for your image distance. That gives you your di, which allows us to solve for the magnification or the hi using the magnification equation. Next, if we use the magnification equation and we input what we just solved for, we can solve for hi, or the height of the image. So in this case, we get the lowest terms of negative 22.5 divided by 45. It's negative 1/2. And we multiply both sides by 4 to cancel out 4. We get the height of the image is equal to negative 2.0 centimeters. So don't forget the units. Make sure all the units are of the same unit. So in this case, it's all the same unit. So we have our answers, 22.5 and negative 2 centimeters. Now we just have to phrase these in sentence form. So the image is 22.5 centimeters away with a height of negative 2 centimeters and it's real, inverted, and smaller. And that's it. That's how you solve your ray diagram problems for your lenses. So beauty is in the eye of the beholder, sometimes literally. There's lenses in your eyes that allow you to see. And sometimes maybe people don't appreciate you because they're not looking close enough. You're not within the good range at which they can see you. So if someone says that you're not good enough, maybe they need glasses, right? So don't let other people judge you. You judge yourself. All right, so that's pretty much it for this topic. I'll see you guys next time.
That is over.